Swayam Prabha. Digital India. Educated India.
Hello, good morning everybody. Today we are going to discuss another concept of vacuum technology, where we will be covering fluid flow in pipes as a part of interconnecting the pump and chamber, etc. It is a general fluid mechanical equivalent aspect, but I should say here, already I told you in the earlier classes, in vacuum technology, as you go down in pressure, the conventional fluid mechanics is no more valid, but initial few minutes it is valid. Some sort of few seconds it will be turbulent flow, then little bit of laminar flow. Afterwards, we are going to enter into a new flow which we do not normally come across in day to day life, that is molecular flow. And in between the laminar flow and molecular flow, it will not be a abrupt transition, there will be a sort of transition flow which is otherwise known as Knudsen flow. All these things are separated based on the relative dimensions of mean free path compared to the characteristic dimension, like we do in fluid mechanics also. So this is very important point that I want you to keep in mind. So today we will be discussing in the first part of this fluid flow module, gas flow in general at low pressures, and then we will also define a parameter called conductance, like electrical conductance, here flow conductance, and finally we will see the topic like effective pumping speed. Just because you connect a pump to a chamber, it will not pump as per your calculations. In between there is a connecting pipe. So, that is to be considered, that is a very important aspect, that is fluid flow through the interconnecting pipe. In fact, it is that only we are going to concentrate today in terms of a concept called conductance. So, naturally in this lecture we will be covering an introduction to gas flow at low pressures, and low pressure means vacuum conditions. Then we will introduce the concept of conductance, and we will also see how this conductance can be felt in vacuum systems, how it is going to affect the pump down times and effective pumping speeds, and type of level of vacuum that you can possibly get at the end of the story when you use a particular pump, or when you use a leaky chamber or a degassing chamber. So, it is a starting point of design aspects involving materials, components, etc. Earlier we have seen pumps, then we have seen measuring devices, then we have seen materials and components. So, with all these things you make a system. In that system you will find lot of interconnecting pipes who will deal with that, and it is that pipe which is going to decide the entire story of pump down. So, that is why this conductance concept and fluid flow concept is very important. I am calling it as a fluid. Generally fluid means either gas or solid in a continuum phase, but somehow it has become popular. In the initial few minutes of vacuum system pump down, it is in the fluid state. Later it is in the molecular fluid, in a way, molecular level. That means molecules are completely independent, they do not have any viscous drag. The classical concept of viscosity is no more there. So, no question of Reynolds number. So, many things are going to change when we discuss flow of molecules. Unless it flows, we cannot evacuate. So, on one side pump, other side chamber, in between connecting pipes, and there may be some couplings, there may be valves. With every element which comes in series with this interconnecting pipe will have its own characteristic conductances. Even the companies who manufacture different components, they also give the conductance values. And this conductance itself is a function of pressure sometimes, and it is not a function of pressure sometimes, and it is a function of diameter of the pipe, it is a function of length of the pipe. So, like that there are varieties of things which we need to look into it when we calculate the conductance. So, that we will see in the conductance in vacuum systems. And once we know the conductance, what will we do with this? We know the manufacturer's pumping speed, and we know the conductances from the interconnecting piping, etc. Use both these concepts together and calculate an effective pumping speed. For that, some manipulations of unit systems we will have to see without violating any physics, and how we overcome all these problems by defining conductance in vacuum technology, we will see now. Okay. Already I have explained to you, but it is very important for you to know or hear this concept of conductance again and again, because once you go into the field, you have already supplied pumps. If you are a manufacturer of pump, somebody has already made the chamber, that is not in your control. The interconnecting piping is in the real thing. End stations are important, not that important. The main road connecting these end stations, that is important. Our track is very important. Same thing here also. I have also explained in the first few classes, as pressure is going down, we are slowly getting a molecular picture when the mean free path is of the order of the dimensions of the chamber. But in flow conditions, it is of the order of diameter of the pipe. Static conditions, it is the dimensions of the chambers, but during flow, that means during evacuation process, for example, then we will have to see the relative dimensions of mean free path with respect to the diameter. Okay. Now, viscous flow we all know, but molecular flow we do not know. So, as you start going down from atmosphere to high vacuum by connecting a pump to the chamber over a period of time, something is happening to the flow of gas molecules from the chamber to this side as a function of time. Initially, it will be turbulent flow, few seconds when rotary pump is just switched on, 1000 millibar. But after, when it starts coming to 1 millibar or 10 millibars, there will be in fact, even within 300 millibars, say, let us say, you will start getting laminar flow, but still it is viscous flow. You all know that viscous flow is separated into turbulent and laminar viscous flows. But very soon, as soon as you come to 1 millibar, etc., you will start getting a molecular picture, and this viscosity concept will go down. And this will be a gradual affair. So, there will be a sort of Knudsen flow, that is called transition flow. All that is shown pictorially here, as the pressure in the chamber is going down from atmosphere to low vacuum and finally high vacuum, that means pressure is going down. The flow in the connecting pipe between chamber connected left side and pump connected right side, that flow slowly shifts from viscous flow to molecular flow. Viscous flow normally occurs when the mean free path is very small, very short, few microns type, that is less than even the characteristic dimension by 100. Here the flow is governed by the viscosity, like a typical laminar flows we in day-to-day life we will see in fluid mechanics. So, if it is quite turbulent, when pump is switched on suddenly in first few seconds, gas is sucked, that time I can say sucked. During that time, molecular tracks, if you observe, we cannot see these molecules, of course, this is a pictorial representation. It will be random, there will be cross motion, etc. So, flowing gas layers are not parallel, that is called turbulent flow, which normally happens at rho v d by mu, which is Reynolds number, is more than 2200. It is not a very clear number or anything, but Reynolds has done lots of experiments and he gave certain ideas. It is really a great work, I would say. he has done with various numbers of diameters, lengths, etc., and various densities and various velocities, and found a dimensionless number. In fact, that was the first successful number with which fluid mechanics has started. Okay. So, first we will have to see which flow regime we are in. This normally happens in vacuum technology from 1000 to around initial few seconds, maybe 400, 300 millibar, like that, depending on the time of evacuation. If you are not giving enough time for sucking, there will be turbulence, not only pressure. But once the Reynolds number starts coming down less than 1200, you will start getting a laminar flow. Laminar flow means the gas is flowing from the chamber to the pump, but gas is flowing a sort of layers type thing, lamina, layer type of flows. This all most of you know, there will be parabolic distribution of the velocity vectors, etc., in a fully developed flow, all that we know in fluid mechanics. So, that is laminar flow. But within few minutes we start coming to 1 millibar and 10 power minus 1 millibar type thing. At that time the flow will be molecular flow. That means, here gas streams are going, but here gas molecules. This is a track of each molecule. Here streams of molecules, they have a continuity, they have a drag. If something happens to some molecules, it will drag other molecules, like that. The drag is missing here, molecular drag is missing. Molecules can be dragged by solid surfaces, we have seen in turbomolecular pump, because most of the time they will hit the solids or the pipe walls or chamber walls. So, naturally they can get additional momentum or braking with collisions from various solid substances located inside the vacuum housing, but within the gas molecules there is not much interaction. So, drag force is not there. So, that way each gas molecule hits the pipe and comes down and again hits, and if the local at this surface, if you zoom it, if the surface is little rough, it may even go back. This may be pump side, this may be chamber side, low pressure, but gas need not go from high pressure to low pressure in molecular flow. But in laminar flow and turbulent flow, always gas flow direction will be from high pressure to low pressure. In fact, pressure gradient is the driving force. Okay. But here it is different. Each molecule has got a free molecular velocity obtained from its thermal energy. We have seen in cryopumping also. At low temperatures, these thermal velocities will be less. At high temperatures or room temperatures, depending on the mass, different velocities will be there. Lighter the molecules, higher the velocity. So, these velocities, and they are far away from each other, they will never hit each other. They may look like nearer to each other, but each fellow will go in random directions. The chance of particle hitting another particle is very less once you cross 10 power minus 3 millibar, which is just the starting point of vacuum technology. You have 10 power minus 10 tar. So, most of the diffusion pump, Roots blower, turbomolecular pump, cryo pump, ion pump, these are all molecular pumps, they are not gas pumps. Okay. So, here it will be tracks will be like that. We have to apply some Monte Carlo techniques, we have to apply some other molecular type of physics, not typical Navier-Stokes equations or typical fluid mechanics equations will not work here. Okay. So, we have to be very careful here. Flow is governed more by statistical picture, molecular picture, etc. Here it will really behave like a fluid, here it is an ensemble of molecules. That is why molecular flow occurs when mean free path is much more than d. That means, this molecule will hit another molecule maybe at after maybe traveling 100 meters, but every molecule will hit first the walls. So, chance of hitting the wall is more. So, average time spending will be more on the walls. This is called molecular flow. It is characterized by the fact that no viscous effects are there and molecules are independent. I hope you have understood. For example, a short hole type of thing in a vacuum chamber, it can be also considered a sort of pipe, small short pipe. If it is a viscous flow or laminar flow, the velocity directions of the gas flow will be like that. It is sort of continuum concept. But if it is molecular, they will be hitting and finally going towards lower pressure. Means what? Finally going to the low pressure, I am telling. At the same time, I say it can go back against pressure. What I am saying is, on an average, this side little high pressure because it is chamber side, this side it is pump side. Molecules will be going in all directions from here. Molecules here also going all the direction, but number density is high here because it is little high pressure compared to less. So, number of molecules going from left to right are more compared to the molecules coming from right to left. This is called molecular flow. So, net flow will be along the pressure drop direction only, that is always there, pressure drop direction only, but not the driving force. It is because of concentration differences, the molecular flux towards left from pump to chamber is always less compared to the flux from chamber to the pump. You should think like that, and in between this molecular flow and this viscous flow or laminar flow, at some transition region you have some sort of continuum concept and also molecular concept. So, this occurs in a region called transition region, okay, Knudsen region, like that. Knudsen has defined a number just like Reynolds number, lambda by d. Okay. This is a very important number in vacuum technology. Even in thin film depositions, we will see the distance between the source and the substrate. If it is d and lambda is very high, then each molecule will go straight away. You will have molecular beams, ion beams. So, all those concepts are again related to this. Okay. We will see that when we come to the applications, but first we have to get the vacuum, and we can get vacuum in 5 minutes or 5 hours. It is to be decided by the pump, of course, by the volume of the chamber to be pumped, by the unnecessary nuisance of leaks or degassing, but at the end it is mainly governed by the interconnecting pipe. You may have very good amount of water or fruit juice, you may have very good lungs, but if you are given a very narrow capillary pipe and asked to, if you want to drink, you cannot drink. You cannot create that sort of action. Same thing here also, it is the connecting pipe that is going to decide the pump down time or pumping speed as seen by the chamber. There may be pumping speed high here when the pump given by the manufacturers, but pumping speed at the other end will be less. If you make the chamber sit on the pump, then you will get maximum pumping speed, but the connecting pipe, that is going to decide. Pump may be 1 crore rupees and chamber may be very high quality chamber with gold gaskets or anything, but even then the connecting pipe, which is only a few hundreds of rupees, that is going to decide the pump down process. So, please keep that in mind. This is how a general gas flow occurs at low pressures, that is our vacuum technology range. So, I told you how to deal with this problem. We have to have some parameters for any scientific understanding or design to predict pump down timings, etc., or ultimate vacuum that is achievable with a configuration containing one pump and one chamber, with and without degas, or during deposition, or during drying, or distillation, or some other source of gas coming from desorption. How do you handle this? Particularly from with respect to connecting pipes, the concept of conductance is going to help us a lot. So, I am again talking the same thing, but it is very important because vacuum system design is mostly related to conductances. Later materials design, components, they are more or less same as high pressure things, and of course, thickness calculations have to be done with respect to bending moment, etc. That is not a big thing, but here it is very big. What we think it is in 5 minutes, but it is coming after 5 hours, and you do not get vacuum after 5 hours, when will you do experiment? So, you have to be very careful in designing the connecting pipes. So, generally vacuum chambers need some interconnecting pipes between the chamber and the pump. Now, this connecting pipe as smooth as possible inner surfaces. Always in vacuum tubes etc., you must keep the inner surface very smooth, otherwise this molecular flow lot of drag and breaking will be there. Okay. If that is happening, if you longer the pipe, then pressure drop will be more, like our standard fluid mechanics. So, in vacuum technology also there will be resistance to flow when pump is connected and switched on from the chamber, but this resistance is the flow resistance. The flow is throughput. I have explained throughput, which is nothing but volumetric flow rate multiplied by the pressure. It is proportional to mass flow rate because pressure is proportional to density. We discussed in the initial concepts. So, that throughput is like a current, it is flowing mass current, gas current or molecular current in molecular flow, and pressure drop is like a potential drop, it is like a voltage. So, current by voltage is conductance, voltage by current is resistance. So, this flow resistance, instead of talking flow resistance in vacuum technology, it is customary to talk the reverse of that, that is flow conductance. Okay. So, flow conductance is defined as throughput divided by the pressure drop, and throughput is tar liter per second, because P dV by dt. Pressure drop is also tar, that way it will have liters per second. So, its unit is luckily matching with the pumping speed unit at any particular pressure, liters per second type thing. That way conductances and pumping speeds can be added, subtracted like that. That is how they have defined the conductances. While looking into physics of the flow, they have made it in such a way that P dV by dt divided by delta P, that is Q by delta P, is called as conductance, and that conductance will be varying in flow regimes. In viscous flow, it will be linearly varying as a function of pressure, and in molecular flow, it does not depend on the pressure at all, because anyway molecules are independent, whether there are 100 molecules around me or 1000 molecules, I am not going to heat anybody, I will heat only the chamber walls. So, that way the flow behavior of this ensemble of molecules is more or less constant, it does not depend on pressure. Okay. So, conductance is a constant in molecular flow, it varies linearly, and in between transition region, which is called Knudsen flow, it will have some characteristics of viscous and also that. We have to add conductances of both these things to calculate the effective conductances etc. Provided we know these conductance values using some other equations involving diameter of the pipe, length of the pipe, like that, then only we can back calculate and find out what will be the effective pumping speed. Once you know the effective pumping speed, what will be the pump down time. If it is not acceptable, either you reduce the length or increase the cross sectional area or increase the pumping speed or decrease the volume or do something or add 2 pumps. So, this is how the designer has to think, engineer has to think. Okay. Now, same thing in a typical system, let us say a diffusion pump system. This is diffusion pump, this is rotary pump, this is a roughing line, this is a backing line, this is a main line connected to the system. We have discussed all these things in diffusion pump time. I am going to show here. That means, there will be connecting pipe in the roughing line. I am showing pictorially a small thing, but it is not small length, it is a quite long length. It will affect the pumping speed of this fellow as seen by the system in the initial roughing. Similarly, it will affect here also in backing. So, we have to be careful in designing these pipe lengths. Now, schematically a chamber, a pump, a connecting pipe. Now, I already discussed with you the conductance is defined as the throughput, that is going from left to right, because chamber is always at higher pressure, divided by the pressure drop P 2 minus P 1. It is current by the voltage potential drop, let us say it is a pressure drop, and this is a flow current, that is also like a charge and particles there, here actual particles flowing. So, this is sort of Ohm's law of vacuum technology, Ohm's law of vacuum technology in flow dynamics, flow mechanisms. Okay. So, this conductance itself, its unit is liters per minute, same as pumping speed, but it is a function of pipe dimensions, which gas is flowing. For the same pipe length, same pipe some other lighter gas flows, then it will have another behavior, because its molecular velocity is very high. Okay. But we are not going to use these velocities like Reynolds number, that is a gas velocity. This is a free molecular velocity, random velocity, which is in all directions. Net velocity is 0 actually, it is moving everywhere. Here like molecules here, molecules are moving with a huge velocity, 300 400 meters per second. Normal pipe flows etc. 20 meters per second. Real velocity of gas is much less compared to the random velocities. This is pressure energy is related to random velocity. The particular velocity is related to the gas velocities in the fluid mechanism. In molecular velocities, it is only these random velocities we have to talk. There is nothing called gas velocities, but in the laminar region of the pump down, there will be viscous drag etc. So, once we know this conductance, since its unit is same as this one, I can get an effective pumping speed available here S effective compared to the actual pumping speed by a simple formula called 1 by S effective is equal to 1 by S plus 1 by C. And this C itself can be calculated using some equations, which we will see in the next few classes. And if you connect several conductances in series, it is like resistances in parallel. So, effective conductance is like that. From the electrical analog you can understand, if the conductances are connected in parallel, then net conductance is C1 plus C2 plus 3. It makes sense, because gas can flow there also, gas can flow here also. It is adding conductance, conductance adding means it is easy to flow. So, I can get faster the pumping speed. Suppose you between the pump and the chamber, instead of one pipe, if you connect two parallel pipes, the pump down time will be half. So, having purchased crores of rupees of pumps and chambers, an intelligent engineer will find some other routes also, just like in traffic jam we will find a parallel route. So, these concepts have to be worked out. Once you know the effective conductance, that means first you get the conductance, individual conductances from the formula, and the net conductance whether they are connecting parallel or series. If there is a network of pipes, you have to use network theory. Once you know that net final effective conductance, you can know the effective pumping speed by manufacturer's pumping speed 1 by S plus the effective conductance 1 by C will give you 1 by S dash, and invert it, use that as the effective pumping speed available in the chamber, and then see what will be the pressure versus time curve. If it is not acceptable, then you will have to do something with the pipe or the pump. Okay. Let us see an example. I am saying the same equation, 1 by S effective is 1 by S nominal given by the manufacturer at a particular pressure. In most of the pumps up to 1 millibar roughing pumps, pumping speed is going to be constant. We will see how to calculate pump down curves using all these formula later. Today we are concentrating on concepts of conductances. That is why I am showing this thing again and again, effect of conductance. So, if you solve this equation, you will get S effective as C plus C into S nominal by C plus S norm. Now, I have given a small exercise. Assume one constant conductance 20 liters per second, assume. Okay. Now, that is constant in all calculations, but nominal pumping speed, that means you connect 0, 0 is always 0, then some small pump, bigger pump 40 liters per second, 50 liters, you can purchase several pumps. All the pumps are connected to the chamber with the same conductance, let us say. Then 1 by S, if you calculate nominal pumping speed given by the manufacturer and conductance, you will start getting effective pumping speed. That effective pumping speed I have calculated here. And when I plot that effective pumping speed as the nominal pumping speed for a constant conductance of a given pipe, you will start getting very interesting variation, that after some time, even if you are having 200 liters per second pumping speed, it is only 18 to 20 liters per second available at the site of the chamber. That means, the manufacturer says I have given 200 liters per second, and you are getting only 20 liters per second, because the connecting pipe is such that this equation has given such an effective pumping speed available at this spot, and which is very small. So, what to do? Either you connect a larger pump, then in spite of the reduction you will still have pumping speed, or you try to minimize length or maximize diameter in such a way, with those dimensions, with the formula you can easily find out conductance will increase. Once conductance increases, that means instead of 20 liters, if it was 40, then curve would have been big, taller side, that side. Okay. So, here just to show the effect of conductance on pumping speed of a pump as seen by the chamber. So, initially after maybe 40-50 liters or when S is of the order of C, till that time it picks up, but afterwards it reaches a constant value. That means, when pumping speed is increasing, effective pumping speed also increases quite good, but when it goes to higher pumping speeds, effective pumping speed is not increasing that good. So, you will get 200 liters by 18 is almost to 11 times, whereas here if you see 50 by 15, so it is only 3 times. So, smaller pumping speeds, small pump connected by a TDS pipe, okay, you will get 1/3 of pumping. But if you connect a larger pump, you think you are getting, but its final effect is only 18-20 liters. So, all the energy is lost, just like pressure drop is a loss measurement in fluid mechanics. Here also it is like that. So, from here what you understand? Conductance is going to play a very important role in vacuum technology. It is the interconnecting pipe we have to design. In the next few classes, we will try to calculate the value of this conductance in molecular flow, transition flow, laminar flow or turbulent flow or choked flow, etc. And afterwards, use all of them in series and find out the pump down of some typical examples we will take, either with source or without source. A chamber evacuation is different. Chamber with source of gas in the deposition, chamber with the source of gas coming in the drying of a pharmaceutical, or that with some particle accelerators. So, things will change, desorption, how these pump down curves are going to change. That means, throughput itself will be adjusted there. Delta P's will be coming out of conductances. When out of that, we will have to finally calculate pump down. So, pumping speed, effective pumping speed along with conductance calculation is going to play an important role in deciding the pump down, which is very important in vacuum technology, whether it is electronics or any other industry, space or nuclear. And high vacuum, it is all the more, because conductance is very poor, you should be very careful. We will see all these steps one by one in the coming classes. We will repeat some of these concepts later. Thank you very much.